Okay, hi everyone. Today is essentially the whole class will be talking about the theorem of Gauss, how to prove it, and some like corollaries and like interesting remarks about it at the end. So that's the content for today. And we will also discuss finally how you should like hold a slice of pizza so that it's not like looking like that and like all the nice juicy things on the pizza are like dripping around. So actually, I prepared like some slices of pizza. I asked the university if I can have real pizza, but they said like better not. Just like give them around, and you can play around a little bit with like how should you hold them so that the tip is not like looking like that. You want like something that it's like kind of like going straight and not falling around. What should you do to this piece of paper so that that it's not like like flapping around. So just try it. Once you have it tried, and just pass it to your next neighbors and like let them think about it. And if you know how to do it, or if you figure out how to do it, explain why that works. Like think about it. Like what is the content with that, with the class, and why does it work? Like if you figure out a way to do it. Then what is like the connection to, for example, the Gauss theorem? So that's just if you're a little bit bored during the class and would like to think about something else. So the theorem of Gauss says that the Gaussian curvature is invariant under local isometries. And the main idea of the proof is to make use of these two equations, or three equations, that we always see. And the first one are the first structure equations, which relate the dual frame, the thetas, to the connection form. And then we have a second equation that says how the connection form is related to the Gauss curvature. That was the Gauss equation. So the idea is in somehow to say like, okay, like analyze how both of these equations transform under local isometries. That's like one way to view what we're doing today. Another way to view is like, okay, like we would like to see how much of these equations are actually determined, for example, omega 1, 2. Is that like the only one that is like acceptable for that, or are there multiple forms that are satisfy these equations? And the same thing, are there multiple like functions there? So that's yeah, like another way to view what we do today. So the main problem is that originally everything was set up with like a whole frame in R3. So that was always the starting point. The issue that we have to deal with is like is that we all was set up to all objects we discussed so far. Say like theta 1, theta 2, theta 3, and then from then we derive the connection forms and stuff like that. All of that depends on a frame defined on U in some open subset. So that's the starting point for all of what we did so far. We always choose some frame, and then we define the dual frame and the connection forms in terms of the frame. But now we would like to kind of like single out what is intrinsic and only depends on the surface in itself. So the idea is to analyze how much they depend on E3. So like we fix, in some way we fix E1 and E2 on the surface, and then we would like to say, okay, like how much do these forms depend still on E3? Especially when we restrict to the surface, so the starting point, or like the point is that we would like to say, for example, that things that only involve coordinates 1, 2, that's the expectation. Like objects involving only the coordinates 1 and 2 are independent of E3. So that's not totally clear a priori. For example, the connection equations have like some components that also relate, for example, to connection forms 1, 2 to something with E3. So that's like not totally clear why that should be like the case. But that's like a bit like the expectation is that at least the hope maybe that things that only involve coordinates 1 and 2 might also like intrinsically defined only on the frame. So the starting point is now for now the starting point for our discussion is that we have vector fields E1 and E2 which are tangent to S. So two tangent vector fields and orthonormal with respect to the first fundamental form. So that's the starting point. And now we would like to, from the previous lemma that we had at the end of the previous class, we had that we can always extend these vector fields E1, E2 to some frame that is defined everywhere. To extend E1, E2 to a frame open subset. So you have this frame, the E1 and E2. You can extend them to like a frame. So like you cannot think of that like you have some coordinates E1 and E2 like that are living on the surface, and now you say like off the surface we can like extend them and change them, and we have like a third vector E3. So now we have some frame which is like really defined on some open subset of R3. Then we can apply our construction to get like the connection forms, the dual forms, and then we restrict everything again to the surface and to see if that then depends only on E1, E2, or if that's really the, something that depends on these choices of this extension. So this is extension is not unique. There's many different ways. You can choose different normal vectors, and you can choose, like you can extend them off the surface in very different ways. So we need to analyze how much that depends on the extension. Okay. So, when we have that, we have two vector fields E1 and E2, which are tangent to S and orthonormal. We say that E1 and E2 are called the tangent frame. So tangent here refers to the surface. So it's really like special to the surface. The normal frame that we had before, they were not making any reference to the surface. Okay, so now we are essentially parallelized the same discussion that we had before. So we have E1, E2 tangent frame on S, and then we can define the dual frame. The dual tangent frame are one forms on S such that they satisfy the equations that you would expect that if you plug in the J's vector in the one form, you get only one if I and J are equal, and otherwise you get 0. So they're like very similar to the dual frame that we have for the normal frame, but here it's really that we have like 1 and 2 because we only need like E1 and E2. So it's like really only forms on S. So that's the difference that we have. And because E1 and E2 are like orthonormal, they form a basis. So this equation really defines the one forms uniquely. So clearly, if you have an adapted frame, or you, for example, you extend these E1 and E2 to like the surface, and then you restrict the theta 1 and the theta 2 that you have from the normal frame in R3, then you get also exactly two forms which satisfy this equation. So then the restriction are the same. And now the first lemma that discusses exactly this point is like how much does like omega 1, 2 is given by the theta 1 and theta 2. So the lemma says there exists exactly one form, let's call it alpha, on S, satisfying these two equations, that if you have d theta, you take the d of that, we get a 2 form. In this 2 form, we would like to express as alpha wedge with the second form, and d theta equals to minus alpha wedge theta 1. So the point here is that we really have like the tangent frame is fixed, then we get like uniquely the dual tangent frame, and that the lemma tells us now that using these two equations we can define the alpha uniquely. So how do we go about proving this small lemma? The proof is we apply E1 and E2, the two vectors that we have, to these equations. So what this means is we have this, this is a 2 form. So if you apply it to the left side, we just get d1, d of theta 1 applied to E1 and E2. That's like, just like a number. And now we do it the same way on applying it to the left side. And then what we get is that using the wedge product and the formula for the wedge product, we have that we evaluate alpha on E1 and then theta 2 on E2, and then minus the ones where we turn around E1 and E2 in the arguments. But in this case, we have theta 2 eating E1, and that gives us 0. So we get a 0 here. And this one is just 1 by definition. So you see that what we get in summary is that it's just simply alpha applied to E1 equals this expression. And similarly, we can do a similar trick applied to E2. The same calculation, we just insert the equation and we get E2. And now we apply it here. And here we see that we have to turn it around. So we get 0 minus, which turns to plus, so it's alpha in E2. So what we see now is that alpha of E1 is given by d theta of E1, E2, and alpha of E2 is given by d theta of E1, E2. So these equations you can now turn around like your viewpoint. Like one way would be to say, if you don't have an alpha, then we define alpha by these two equations, by saying like alpha E1, alpha E2 equals the left-hand side. So that would be one side to define alpha. So that's like the one direction. Would be define alpha. These equations, which is definitely sufficient because E1 and E2 are bases. We only need to say what the value of alpha on these basis elements are. And conversely, if you have alpha that satisfy these equations, so there would be like the uniqueness, maybe existence, and uniqueness follows also because alpha clearly has to satisfy this equation. So if you if you have multiple, like the left-hand side doesn't depend on alpha at all. So Okay, so that shows that there exists exactly one form under S that satisfies these two structure equations. So that allows us to formulate as a definition. It means exists the unique one form satisfying both of these equations. Let's give them one form alpha is called the connection form. Associated with E1 and E2. And we write alpha equals to omega 1, 2. So it's like you might be a bit confused because we already had omega 1, 2. But this one is like slightly different defined. Like the omega 1, 2 that we had already were defined as like take the E1 and take the variation of E1 and then expand that for the frame. But there we was like expanding it with respect to the frame E1, E2, E3. What we do here is we start with a tangent frame. We define the one forms on S, which are like the dual tangent frame, and then we define omega 1, 2, which is only a one form on S by these equations. So that's a slightly different viewpoint. Of course, once you have the connection form in the sense of E1, E2, E3, and you restrict it to S, you get exactly a form that satisfies these equations. So then that's exactly the same form here. But like our viewpoint here is now slightly different, that we really start intrinsically just working on S. We don't care about E3 at all. There's like all of these two blackbirds doesn't make any like mentioning of E3. So these are like completely things like intrinsically defined on the surface. So that's the whole point of the exercise, that we just work on the surface. So the point here is also, if you turn it around, is that this lemma shows you that omega 1, 2 on S only depends on E1 and E2, and that's only on the first fundamental form, and not the second fundamental form, or on the operator, the shape operator. So that's an important observation, that at least when we restrict to the surface, we get something that is independent. Okay, so the first lemma was saying that these equations define the alpha uniquely, and now we would like to say, of course, that the connection, that the Gauss curvature is also uniquely defined. So that's the second lemma. There exists a unique function K on the surface such that d omega 1, 2 equals to K omega theta 1 theta 2. But this one is now the connection form 2 is the connection form of the tangent frame E1, E2. And the proof is very similar as before. We just evaluate both sides on E1 and E2. Equation on E1, E2. So what we get is that it's d omega 1, 2. It's a one form, two form, which we evaluate in two vectors. And then you have k, that's just like some function, and then we apply theta 1 wedge theta 2 to E1 and E2. And now we use the same thing with the wedge product, and we say like only the term where theta 1 applied to E1 survives and theta 2 to E2, which gives us each time just like 1. And if you turn it around, you get 0, because then theta 1 is eating theta, E2, which gives 0. So that gives us k. So that gives us the equation how to get k once you know d omega 1. So you just know omega 1, you take d of that, you apply E1 and E2 to it, and then you get k. So that in particular means that there's exactly one k that satisfies this equation. So the same thing applies in here, is that that in k, the Gauss curvature only depends on the tangent frame E1 and E2. So that's already an important observation, and that essentially like the first hint why you would expect something like the isometry preserving of the Gauss curvature to hold, because if that k depends only on the tangent frame in a nice intrinsic way, and our local isometries are actually made to preserve, at least not like they preserve E1 and E2, like not like on its nose, but they transform E1 and E2 again to a nice orthonormal frame with respect to because they preserve the metric. So they will map nicely tangent frames to tangent frames. So that means that there will be a hope to also relate the curvature, the Gauss curvature under local isometries. And to make that a little bit more precise, we need to discuss how these equations actually transform under local isometries. Behavior from E1, E2, P1, P2, and omega 1, 2 under local isometries. So that's the idea now, is that we know the curvature is is like uniquely defined by the connection forms, and the connection forms are uniquely defined by the dual forms. So let's analyze what happens of all of these objects under local isometry, and once we know that, we might plug everything together to get like the behavior of the Gauss curvature under local isometries. And that's the next lemma that tells us how this is done. So we have F, which is a local isometry. So the local isometry, you can think of that as like a sheet of paper. That's like S. It's like a flat sheet of paper, and then you bend it, and that might be a S tilde. And then let E1 2 be a tangent frame on S on the first surface with dual frame theta 1 and theta 2 and connection for omega 1, 2. So these are all bond forms on S. And then the lemma says the following. First of all, if you push forward these vector fields E1 and E2 by F, you get another vector fields on a S bar, and they turn out to be orthonormal again. So that's the first one is that E1, E2, which are defined as the push forward. So equals tangent frames on S. So E1 and E2, which you just like insert E1 in the tangent map, and you push it forward to get like a vector field. Maybe to make it like easier, just say that it's a complete isometry. And then we get like two tangent vectors again, or two vector fields on S bar. Then these ones are tangent frames on S bar, meaning they are orthonormal with respect to the second fundamental form on S bar. So that's the first result. So now we have two tangent frames on S bar. So we get like the dual frame and the connection form on S bar with respect to these frames, which then are satisfied. Dual tangent frame on S bar associated with E1 bar and E2 bar is uniquely determined by, so the dual frame would be theta 1 bar, theta 2 bar. So these two forms, they are uniquely defined by taking, so these are one forms on S bar. So what we can do is we can pull them back to S by F to get a one form on S. And then it's like the natural thing is what you expect is that these ones are exactly the forms that we started with. And then the third point third point says that the connection form from omega 1, 2 bar on S bar associated with E1 bar and E2 bar is given by uniquely determined by the same equation, kind of form of the equation. And we say we pull back the one form on the S bar back to S to get a one form, and this one we compare, and it turns out to be equal to the connection form that we started with. So the proof turns out to be quite simple once you are like a bit familiar with the pullback operations and like the acrobatics that we learned about. So the proof is, the first one is we have to show that these vectors that we define here, E1 bar and E2 bar, are orthogonal with respect to the second, to the first fundamental form. So let's plug them in and see what happens. So E1 P bar, E2 P bar. So we plug them in and see what happens. So we use the definition of how they are defined, namely in terms of taking TPF of E1 of P, and then taking TPF of E2 of P, and then plugging them in the first fundamental form. So now you realize that this expression here is nothing else than the pullback of the first fundamental form by F evaluated on the vectors E1 and E2 of P. This one is the same thing as the pullback of the first fundamental form of the surface evaluated at the point P, and then E1 and P and E2 of P. So that's awesome because we know what this one is. It's by definition it's an isometry. So what we can do here, we can write this just as the normal first fundamental form on S, because that's the definition of an isometry. But that it's nice because we know that I applied to E1 and E2 just gives us, maybe I should have, yeah. So this one would be 0. So now let's do the same acrobatics for I and J. So it would be I, J, I, and J, I, and J. So that gives us 1 if I equals to J and 0 otherwise. And that's exactly what we wanted. We wanted to say that E1 and EJ, if you plug them in the bar of first fundamental form, we get like exactly 1 if they are like the same, and otherwise they are orthogonal. So that implies that E1 bar, E2 bar orthonormal with respect to. So this one here, I confused you last time. That's maybe I write it out first. With respect to. So it's like short form of like with respect to, and that is with respect to the first fundamental form on S bar. So that's the proof of the first statement. second and also for the third property, it's enough to check on the basis. Enough to check the equality there that the pullback of theta 1 bar equals to theta 1 on a basis or on the because they are a nice orthonormal basis, we can just like evaluate this equation on E1, on E2, and then check if both times it works. So let's do it slowly. Say we plug in E1. What we get is at some point P, we just use the definition of the pullback, which says that we take push forward the vector, which means that we take tangent map of the E1 of F applied to E1. But this one was by definition E1 bar F of P, and the theta 1 was the dual element of that. So this one is just like 1 because that's the definition of the dual. And similarly, we can apply at this time to E2. We do the same trick. TPF of E2. In this case, this term is nothing else than E2 bar at the point of P bar. And theta 1 applied to E2 gives us 0. So we get 0. But this one is exactly the definition of the one form theta 1. It's like theta 1 is uniquely defined to be this one form that if you evaluate it at E1, you get 1, and if you evaluate it on E2, you get 0. So that means that we have F theta pullback has to be the one form phi1. And very similar, we get just the pullback of E2 equals to sigma 2. Maybe using exactly the same equation, but just changing the numbers. So that's for showing 1 and 2. What about E3? Oh, it's actually over there. The third one. So now let's look at like the proof of the third point up there, which says that also the connection form are nicely related under isometries. And for that, we had like nice propositions last time, namely that F star of alpha wedge theta equals to F star of alpha wedge S star of beta for one forms alpha and beta on S star. So that was one result that we learned, and another one is that alpha of d alpha equals to d of the pullback of alpha. So that was some of the properties that we discussed last time, that you have under pullback, we have such nice equations of the wedge product and also of the exterior differential. And using these equations, we can apply now to calculate what happens to the d theta 1 bar. So we take theta 1, apply that, the d to that, and then the pullback. So let's calculate that in two different ways. So the first one would be just using these properties, where we get that it's d of f bar pullback of theta 1, and this one we know is like d of theta 1 by definition of by point 1, by property 2. So that's the first way, but we can also say f bar is also, we can also say, using the connection form, we can say that this guy here is given by omega 1 2 bar wedge phi star 2. So that's the definition of essentially the definition of the connection form is that d theta 1, you apply d to it, you get like the connection form. So now we have to calculate that. For that we use the first property, where we can say that f star of theta 2 applies to f star theta 2. And this one here, we can again write as phi 2. So the upshot here is that we have d theta 1, if you read it like from here, d theta 1 equals this guy, but this guy also equals this guy over here. So we get f star omega 1 2 wedge theta 2. And similarly, we get like a same kind of equation, but just with like the numbers reversed. We get f star omega 1 2 wedge phi 1. But now it's no longer on the blackboard. But we had had before that these equations, they are uniquely, if you have like a one form that satisfies d theta 1 something with alpha wedge theta 2, and similarly d theta 2 equals to minus alpha wedge d theta 1, then you can conclude from this that these one forms are like equal to the connection form. So that means omega 1 2 equals to omega 1 2, because these equations are uniquely determine the connection form. Okay, so that's what we wanted. Okay, so that's now we understand using this small lemma that we have here is that we know how to transfer tangent frames. Maybe we just push them forward, and once we do that, we know how the dual frame changes, namely we have to pull them back. And similarly, connection forms, we also have to pull them back and get the connection forms again. So that lemma tells us like completely what we need to know, how like tangent frames behave under local isometries. And that's what we now can use to come back to the proof of the Gauss theorem, which now turns out to be quite simple and straightforward.